Okay, so chapter 24 practice quiz. A soft drink company is conducting research to select a new design for the can. A random sample of participants has been selected. Instead of a typical taste test with the two different sodas, they actually give each participant the same soda twice. One drink is served in a predominantly red can, the other in a predominantly blue can. So think about like Coca-Cola versus Pepsi, okay? But it's the same soda inside the can. The order is chosen randomly. So the first person might have a red one than the blue, other person might have a blue than a red. It's all randomly chosen which one they have, but remember they have the same soda, just different colors of cans. Participants are asked to rate each drink on a scale of 1 to 10. Thus, the company wishes to test if the color of the can influences the rating. The ratings were recorded for each participant. The data are shown in the table below. So, does the sample indicate that there's a difference in the ratings? Test an appropriate hypothesis and state your conclusion. So, looking back at our notes, okay, what we're supposed to do is make a new column where we find the pairwise difference, okay? We basically line them up left to right and just subtract, 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 subtract. Okay, and then we're going to make some sort of null hypothesis that says that the average difference is 0. Okay, and then we're going to use very similar looking standard error of our average difference and our p-value. Okay, our degrees of freedom is just going to be how many pairs we have, right? How many differences do we have, and subtract 1. So very similar to what we did before with our degrees of freedom. Okay. So I'm going to go through here and I'll just call this delta for my difference. Okay, red minus blue. I'm going to say 4 minus 6 is -2, 7 minus 5 is 2, 3 minus 6 is -3, 8 minus 9, -1. Okay, going down the list here, it's just simply this minus this all the way down. Okay. All right, so as you can see, I just made a list. I'm going to do a quick double check. 4 take away 6. Yeah. Okay, so that's the first thing you should do. And now what we're going to do is we're going to be using these numbers. So no longer 2 sets of numbers, just 1 set of numbers. And we're going to do a one sample t-test given this right here. And we know our n is going to be 16. So they kind of help us out with that. So before we calculate this, let's go ahead and set things up. Let's do things we can do without a calculator. And we can start by saying, well, our hypothesis, our null hypothesis will be that our average difference, okay, our mu d, the average difference, we're predicting is going to be 0, that there is no difference between what people said for red and blue. And on average, will this equal out to 0? Okay, now we know when we calculate this average difference, what we should get is probably not perfectly 0, but is it close enough that we can make a determination that they're the same or not, or at least possibly the same or possibly different. So remember, for our alternative hypothesis should look exactly the same, but the symbol is going to be different. Are they saying that the red or the blue is going to have more of a reaction? Like, what are we trying to test? We're simply trying to test if they're different. Okay, is it equal or not equal? So that's where we're going to put the mu of our difference will be not equal to 0. So either it's going to be 0, meaning no difference, or is it not equal to 0, meaning, you know, the red or the blue is favored over the other. Let's take a look at our sample size. Our sample size was 16. That means our degrees of freedom will be 16 take away 1, so 15. They didn't give us an average. They didn't give us standard deviation, none of that stuff. So we're going to have to calculate all those values. Okay, we need those numbers to calculate like our standard error, right? In order to do like this equation, we need our standard deviation of our difference. Okay, we're going to need that number. We're going to need our average. Okay, our delta naught is going to be 0. Okay, that's going to be that value there. Okay, so to take a moment, let's type these numbers in. We're going to say -2, 2, And then I'm going to double check this because I don't feel 100% confident in myself that I'm typing this out correctly. It's just kind of weird. I don't know. I guess I've got to double check this. So let's start off and let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Negative, positive, negative, negative, positive, 0, negative. Okay, so it looks good. Now it says the test mean. So what are we trying to compare this against? And we're trying to go against 0, and it's already set up for us as the test mean. That's kind of what we're trying to test. What kind of average are we trying to test against? So I hit submit, and it gives us these numbers here. The observed difference, sample minus the test mean, is negative 0.375. Okay, so we can say our average difference was a negative 0.375. So if you think about that for a moment, if the average was 0, that means these numbers were pretty much the same, okay? If it was a positive, that would mean the red would be bigger. So positive, sorry, a bigger number, like if this was like, see how 4 minus 6 was a negative, but the 7 minus 5, so the bigger number being on the red side gave us a positive number. But a bigger number on the blue side gave us a negative number. So having a negative difference meant that the blue cans were generally favored. More people voted higher for the blue cans out of that test of 16 people. But is that convincing enough? Okay, so we have our standard deviation of our sample, okay, and that would be 2.029. So I could, from this point, do my equation to figure out my standard error of my difference, average difference, but I'm going to go ahead and take their word for it and say that it's this number there. So I can say the standard error of my difference, of my average difference, is going to be 0.5073. Degrees of freedom, 15, we have already identified that. Now our t-value. So once again, this little equation right here, without it, it's essentially this number divided by the square root of this number. So this number divided by 4. Okay, makes sense that it's 2 cut into 4 pieces with about a half. So that seems to work out perfect. Our t-score, based on our sample size of 16 with the degrees of freedom of 15, average difference minus 0 divided by that number. So it's going to be negative 0.375 divided by this number is going to give us our t-value. Okay, our t of 15 is going to be a negative 0.7393, meaning, if remember a t-value like kind of like a z-score. Okay, if the z-score is 0, that means your value you're looking for is right there at the average. Okay. If you have a positive z-score, that means your value is above the average. A negative z-score means that it is below the average. So if our average is supposed to be 0, it makes sense that since our average was negative, that our t-score would be negative too. It's little things to kind of check our work to make sure we're doing everything right. And once again, all those could be found by using those equations, but we've got a calculator. It already calculated it for us. There's no reason to do it again. Okay. If we were in the classroom with the calculators, we would just be doing this. We probably would never do it by hand, except for maybe in an example. So the next part now is finding our probability of getting a t-score, degrees of freedom of 15, that is essentially not equal to this number here. Okay. This is now, we can go to our table, do these other fun stuff. I'm just going to look over here to where it says sample data is not equal to 0. The p-value, which is our probability, is a 0.4712. So what that says, okay, remember if we want to describe what the p-value is. This is the probability that if there was actually no difference in people's opinions of the red versus the blue soda cans. Remember, the sodas are the same taste. So on a taste test, they found on average the blue can was slightly more favored. But according to this, okay, if this was true, where there is no difference, okay, remember the null hypothesis, if this is true, this is the probability that we would get these or extremely similar results. Probability is 0.4712. That means that's like a 47% chance. That is a very high chance of getting numbers similar to this, okay, or an average difference similar to what we got here of negative 0.375. So it's very close to zero. It's just slightly leaning towards blue. And I'm assuming it'd probably be very similar. If it was like a positive of this number, we'd probably get the same number of this. Okay, it's very likely, if it's true that there's no difference, then when we did this test, we would get those results. So it's a very, very, very high probability. Okay, that's like flipping a coin. That's 50-50 chance. You can't get almost better probability than that. Okay, outside of like 100%. So since it's a very high chance, remember, we're thinking about if that number is less than a 0.05. That's what we're testing for. If it's less than this, we can basically cancel out the null hypothesis and say the alternative is true, that they're not equal to each other. But the fact that it's such a high number, that's pretty convincing evidence that the null hypothesis is true. Okay, we're not going to say it's true. We're just going to say that we're going to fail to reject. Once again, the evidence is very in strongly favor. It's very, very strong favor that this is actually zero or extremely close to it. But we don't say that it's true or perfect or whatever, it's accurate. We're just going to say that we don't have the evidence to say that it's not true. Okay, we're going to say this. So we're going to make a conclusion. We should fail to reject the null hypothesis. Okay. And we'll make a quick little statement that says the chance that the chance that the blue cans had a small but in what am I being so silly right now? A small but insignificant difference is about 47%. Okay, so the chance that the blue cans had a small but insignificant difference is about 47%. Okay, that is a really big chance that the blue cans would have a small but insignificant difference. Okay, 0.3. Okay, that essentially means almost all of these numbers are the same. Okay, with the exception of, on average, the blue cans get a slight itty bitty lead. Okay, but it's so insignificant that we just don't have the evidence. Okay, so that's it. That's all we have to do. So one more time, what were the steps that we did? Okay, we started by obviously reading through the problem, but we were given this table and it said rater 1, 2, 3, all the way to 16. So this is the first person set of scores. They said the red can was 4, the blue can was 6. The difference is 4 minus 6, which is -2. And I did that all the way down to all 16 pairs of numbers. Okay, these are pairs. They're not just random sets of numbers. Like it's not just one set and set 2. These are actually paired up. This person said this and this, the difference was that. And we did that all the way down. I typed those numbers into this calculator and hit enter. Okay, and I double checked. I was testing against a mean of 0. And then all these numbers, okay, sample size 16, means -0.375, standard deviation of 2.029. So when I'm saying D bar, which is the average difference, that's my mean. when I'm saying this lowercase s with a little d here in the corner means the sample standard deviation of my difference is 2.029. My standard error of my average difference, which we have a formula for it, we don't even have to do this now because the calculator does it for us. It's right over there. The t-score that we got, okay, was negative 0.7393. Once again, I could have used this formula. I decided to just use the calculation they already gave me. It's probably more accurate than what we would do. And the probability of getting this t-score, if this was true, okay, would be a 0.4712 probability, okay? All right, so remember, we're trying to test this number here to be less than 0.05, and this is much larger than 0.05. It's almost like 5 cents versus 47 cents, okay? Or like if somebody said, hey, you wanna buy this for me? Sure, how much does it cost? $5. But then you go and it's $47. Like, dude, it's kind of a big difference, okay? So 0.05 versus 0.47, much bigger difference. So we would fail to reject the null hypothesis. You reject when it's less than 0.05. We fail to reject, and I'm making one more little statement that says the chance that the blue cans had a small but insignificant difference is about 47%, okay? Meaning we're pretty sure that if we did this test over and over, it's going to keep being close to 0, okay? All right, so that's it. All you're trying to do is test that and make a determination, okay? All right, I will upload this video and I will upload this document as a, just to help you guys with your notes and stuff, all right? Your quiz will be posted sometime later this morning, okay?